The next topic is graphs of functions. We have already seen quite a few examples of functions, primarily real valued functions, because that is the type of functions we will be interested in this book or in calculus in general. So next we see the graph of a function. Now it goes like this: the graph of a function f is the graph of the equation y equal to f of x. The function f will be given by some formula. That formula can be used to form an equation like this. And we already know how to draw the graph of an equation. So we are defining the graph of a function in terms of the graph of this equation, okay, where f is the function. It consists of points in the Cartesian plane whose coordinates x, y are input-output pairs for f. What this simply means is just this. Say you have the graph of this equation. Then if you choose any point x, y on this curve, then this give an input-output pair for f, in the sense that if our input is x, then the output is y. Conversely, if you take any input x, say x prime, and you find that the output is y prime, x and x prime of course have to be chosen from the domain of f, otherwise f of x or f of x prime may not make sense. So if this happens, then x prime y prime will be a point on this curve. So that is the meaning of the graph of the function f. Now we have already seen graphs of several different types of equations, but the thing that one should note is that not every curve you draw is the graph of a function. And the reason is this: a function f can have only one output for a given input x in the domain of f, because that is the uniqueness of the output. If we give some input in the function, in the formula for the function, then we should get only a single output, not more than one output. First of all, we should get one output, and that output must be unique for that given input. And that is why no vertical line can intersect the graph of a function more than once. This is an example. Okay, it's a circle cannot be the graph of a function, since some vertical lines intersect the circle twice. To be more specific, I have taken the unit circle which has radius 1 and it is centered at the origin. Now this is not the graph of a function, because this equation does not determine y uniquely as a function of x. The reason is clear. If you try to solve for y from this equation, you get two distinct expressions actually. So accordingly, for a given value of x from the set of permissible values, because you see here that x cannot be less than -1, and also at the same time it cannot be greater than 1, because otherwise the expression inside radical, that will be negative, and y will no longer be a real number. So from the permissible values of x, if we choose one value, then y has two values which usually are distinct. Only when x is -1 do you get a single value of y, or when x is 1. For other values of x, you get two values of y for each such value of x. For example, if you take this very simple value x equal to 0, then you get two values of y from this relation. 1 and minus 1. So geometrically, correspondingly, this vertical line intersects the circle at these two distinct points. That is, for the given value x equal to 0, you get two distinct values of y. So y is not a function of x according to this equation. Okay. Similarly, if you take x equal to 1 over 2, okay, 1 by 2, then also you get two distinct values of y such that these points lie on the circle. One of them is square root of 3 by 2, the other one is minus root 3 by 2. So that is why the circle is not the graph of a function. In general, if a is in the domain of a function f, not the circle, I mean any function, then the vertical line x equal to a, which is at a distance a from the y-axis, on the left side of y-axis or on the right side, that will be determined by the sign of a. If a is negative, the line will lie on the left of y-axis, otherwise on the right of y-axis. If a is equal to 0, then the vertical line is the y-axis itself. Okay, fine. If f is a function and you have its graph, then for any point a in the domain of f, this vertical line will intersect the graph of f in this single point only, a comma f a. That is not happening here. So that is why the circle is not the graph of a function. Like that, we will come across in the exercises also at the end of this chapter some curves which are not the graph of any function. Now, how to draw the graph of a function? That is the next thing. So here we take one example 4. Graph the function y equal to x square over the interval over this closed interval minus 2 comma 2. We first write the steps and then we will proceed accordingly. So since this has been given as a question, or rather as an exercise, so we write solution. Step 1, you already know these things, but still let's again look at them in a systematic manner. Make a table of xy pairs xy pairs that satisfy the function rule. Which in our case is y equal to x square. In this case, the equation y equal to x square. So that is step 1. Then step 2, of course, you have to plot the points whose coordinates appear in the table. whose coordinates appear in the table. And then step 3, draw a smooth curve through the plotted points. And finally, label the curve with its equation. Okay, so let us do this now for our given function, which is the square function considered in this interval. That is, we have restricted the domain. We know that the function y equal to x square or fx equal to x square, it has its natural domain is the entire set of real numbers, because if we take any real number as input, we get a unique real output y, which is x square. But we have chosen to restrict the domain to this subset of the set of real numbers. So in step 1, we have to make a table of xy pairs. So let us do that first. For simplicity, we will take only a few points now. And then a natural question will arise in step 3. In executing step 3, we will come across a natural question which we will answer later in the book. But it's a very important question. So this is x and y. This one, 0, 1, 2. Okay. So these are the xy pairs. Okay. So if we take -2, then if x is -2, then y is x square, so it will be 4. If x is -1, then -1 square is 1. When x is 0, y is 0. 1, 1, 2, 4. Then in step 2, we have to plot these points. So let us draw the axis. One, two, three, 4. Okay. One, two, three. 1, 2, 3. -2, -3, this is the origin. 2, 3, 4. So if x is -2, then y is 4. 1, 2, 3, 4. So this is one point. When x is -1, then y is 1. When x is 0, y is 0. Then when x is 1, y is 1, and finally when x is 2, y is 4. Okay, so these are the plotted points. This is one point, this is another, this one is another, this one is another, and finally we have this one. Now draw a smooth curve through the plotted points. Usually from experience we know that the smooth curve is supposed to be something like this, which I have not been really able to draw it properly, but you can understand what I am talking about. Very vaguely we can say that the curve should fit the plotted points as nicely as possible. These are of course not mathematical terms, because as nicely as possible, this is not something that you can quantify. Okay, I mean you can, but not in this vague manner. Roughly we have, in fact you can see here I messed up a little bit. It will not be like this. The rough shape of the curve is like this. But the question is, how do we know how the curve looks like between two consecutive points? Because we are we have plotted only finitely many points. So you will get one point after another, you will get consecutive points. We don't really know what is happening, or we have not cared to know what happens between -2 and -1. Say if your x is here, okay, say x is -1.5, you can of course calculate, you can put x equal to this value and you can calculate y. It will be 2.25. So this point should have coordinates -1.5, 2.25. Have we really been careful to draw this curve so that the curve passes through this point? We can't say for sure, because we have drawn it as nicely as possible. As nicely as possible really has nothing to do with 2.25. After drawing the curve and after putting these values, only we have come to know that this output should be 2.25. Okay, fine. Then you say, okay, so we have taken care of it here. So correspondingly on the other side also, say we have taken care of that. But then what happens between -2 and -1.5? That also we don't know. And in fact, what happens between -1.5 and -1? There are infinitely many values of x that can be chosen as input. So should our table be infinite? Should it contain all the pairs? Ideally it should contain all the pairs, but that is impossible. No. How can you do that? You cannot do that. Even if you continue to take more and more points, yes, your guess for the graph, for the actual shape of the graph will become better and better the more points you take, but you can never really get the job done simply by plotting points. Then what to do? And what is the guarantee that the graph does not look like this? Say these are the plotted points. say we have, in fact, here we have taken care of this pairs minus 1.5 comma 2.25 and 1.5 comma 2.25. Even after passing through those points, this is also a possibility, no? Draw a smooth, okay, we have been asked to draw a smooth curve, so this is not smooth, it has jagged edges. Okay, fine, we can draw a smooth curve and still have messed up results like this. Here we don't have any sharp jagged corners, so it is a smooth curve, but we don't think this is the graph. Why? From experience we think this is not the graph, this is the graph. But why? How does one know for the first time that this is the, or how does one know for sure that this is the way the graph is supposed to look? That question cannot be answered simply by thinking of plotting more and more points, but it needs calculus. Okay, the answer needs calculus, and that's why there is this paragraph. How do we know that the graph of y equal to x square doesn't look like one of these curves? Some such very ugly looking curves are there, all of which pass through the plotted points in the text, but none of them is this graph, like the one we have drawn just now. For the sake of presentation, I will just roughly draw a few. I don't remember at this point exactly how the author has drawn the messed up curves which look like this but which are not equal to this. So I am just going to simply draw my own. So these are okay. So these are the plotted points. We have plotted 5 points now. One may choose to join them by straight lines. That is also a possibility. Or something else like this. Okay, you get the point. One of these curves. In fact, no one knows. To find out, as of now, we don't know. To find out, one could plot more points. But the basic question still remains. How would they then be connected? Those more plotted points So the basic question remains, how do we know for sure what the graph looks like? If we cannot plot all the points, or looks like between the points, between the plotted points, the reason the graph passes through the plotted points is that the collection of all such pairs is the graph. So naturally the entire graph should contain those points in it. So that's why we join the points. But again the same thing, how does one know that it just goes like that in between these 2 points? So this question cannot be answered unless we take the help of the notion of derivative from calculus. The answer lies in calculus, as we will see in chapter 3. And there we will come across derivative. There we will use derivatives to find the curve's shape. Between plotted points. You may be getting some disturbances, some background noises there. There is traffic, something else. I usually film these videos during night time, but last night it was not possible due to the festivities, so I have decided to do it during daytime, okay, for this video and for another number theory video. This will not continue. I mean, it's only one occasion, 1 or 2 occasions where I am compelled to do it because I don't want to lose the days. So usually it will be at night. But before we get to this notion of derivative, meanwhile we will have to settle for what we have right now, plotting points and connecting them using that vague term as best as we can. one thing is clearly true: the more points you plot, the better the shape of the curve you know. And that is because, unless of course that is not always the case, if the curve is not abruptly changing between two very close points, then the more points you draw, the better the shape of the curve will be revealed to you. No matter how much we think of it, we cannot settle it simply by thinking of geometry or in terms of algebra like this, by simply using the equation of the graph, the formula for the function, and drawing the graph. Simple algebra and geometry will not settle this question. Calculus is needed. Okay, now next we see the rough shapes of some known functions which will be of use to us later. The following figure shows the graphs of several functions. Shows the graph of several functions that we will frequently encounter in calculus and elsewhere. Elsewhere means usually, in usual application of mathematics. So let us see some of these graphs. The first one, of course, is the square function, and alongside the graphs we will write the domain and range of the function also. At least we can use the ruler to draw the axis properly. So here the function is y equal to x square. The domain is the entire set of real numbers, and the range, the set of all output values, of course, is the set of all non-negative real numbers. Then the cube function, that was the square function, and now we draw the graph of the cube function. X, y, it is roughly like this. I am showing the general shape, okay. How exactly the function is going through the origin, we are not taking those things into account. You can of course use a graphing calculator, or you can plot also by making tables and then plotting points and then joining those points. That way also you can see exactly how the graph looks. Using a graphing calculator is much better. Online graphing calculators are also available. You can search on Google, you will come across, if I am remembering correctly, there is a site, you just start look this up, Desmos graphing calculator. The first search result is the thing that I am talking about. It is a very nice site. So this is the graph of y equal to x cube. In this case, the domain is again the entire set of real numbers, but unlike the square function, the range is also the entire set of real numbers. Then next, the non-negative square root function. Its graph is okay. This one I have drawn somewhat much better than the other ones. Square root of x. In this case, the domain is the set of all non-negative real numbers, and because we have square root, you cannot take negative inputs. The range is also, it turns out, the same, the set of non-negative real numbers. Then after this, we cannot say before or after, just some graphs, that's all. Then there are some other powers of x. For example, this fractional power. The function is y equal to x to the power 2 by 3. Its graph looks like this. Here I can at least say one thing. This height grows, okay, it does not stay constant, it does not level out after some stage. This height grows and it keeps on growing without bounds. Also, just like this one, okay, we have this one. Although the shape may look the same, but the graphs of course are not the same. If you cut and paste this one here, these two will be different, they will not coincide. The previous drawing was somewhat faulty in the because I drew it like this, as if it's going down. No, it never goes down. It in fact never becomes constant also, it keeps on growing. Then cube root of, okay, so what is the domain here? The domain of course is the entire set of real numbers. It's very easy to see from the graph, that's why graphs are drawn in the first place. You can see many things, not only that they are passing through some specific points and all those things, but you see here the domain is 0, infinity, because on this side of the, on this part of the x-axis the graph lies. You can take x equal to 0, but you cannot take these values of x, because then you will have a negative real number inside square root, and that is not a real number. From the graph you can see that it does not, no part of the graph appears on this part of the x-axis. So this is the domain, and correspondingly the values of y, okay, is all of them are above the x-axis. One value of y of course is on the x-axis at the point x equal to 0, and that value of y is y also equal to 0. The other values of y are all positive, so the range is also this. In this case, using that same logic, the domain is R, because unlike this one, here on the negative part of the x-axis also we have the graph, a part of the graph, but a range like before is 0, infinity. Then cube root of x. This graph goes roughly like this. In this case also, because of this entire expanse, the domain is R, and the range, just like this graph, it keeps on descending without any bound, and this part keeps on ascending without any bound. So the range is also R. I think my logic is correct if I am, yes. Then next, the reciprocal function. Here the function is y equal to 1 over x. For this function, obviously the domain is not the entire set of real numbers. The problematic real number is x equal to 0. For that is the real number which has no reciprocal. So at x equal to 0, the function is not defined. So at x equal to 0, there is no point on the graph. If x is greater than 0, then as x increases, y stays positive, but y decreases because 1 over x. And as x decreases, it becomes closer and closer to 0, y increases. For example, if your x is a very small number like 1 over 100, x is 1 over 100, okay, keep that in mind. Then y is 100, then y becomes extremely large. Like that, if x is 1 over 10,000 suppose, then y is 10,000. Like that. So that's why this part of the graph rises steeply, and the steepness itself keeps on getting more and more. Just like that, on the left side we have the same thing, similar things happening, but because of negative x and also negative y, the graph it dips. The closer you come to x, you get the closer you come to 0, you take x close to 0 but on the negative side of the x-axis, then y is also negative but y becomes numerically large. So instead of taking say x equal to 1 over 100, you can take x equal to minus 1 over 100, then y will be minus 100. Okay, and if x itself becomes very large numerically and negative, then y becomes smaller. It still stays negative. This graph, or rather the two parts of it, none of them touches any of the axes. It keeps getting smaller and smaller, this height, the further you go down the x-axis towards the positive side of the x-axis, but it will never touch the x-axis, because for no value of x does y become equal to 0. Some people like to think of this situation in terms of x becoming infinity, and at that point y becomes 0. Fine, but infinity is not a real number. So infinity is not a point in the domain of this function. So 1 over infinity is 0. At least at this stage we should not think like that. We are dealing with real numbers, so infinity and minus infinity are not to be considered in these situations. They are not real numbers. Okay, under no circumstances are infinity and minus infinity real numbers. Okay, anyway, so here the domain is the entire set of real numbers from which 0 has been removed. You can also write this same set like this: union of these two open intervals, and range, just like that, is also the same. Y takes on all positive values as well as all negative values, but y never becomes 0 because x cannot become infinity. So that is the reciprocal function. So we have seen the square root function x to the power 2 by 3, the reciprocal function, and then another such function which is not the reciprocal of x but the reciprocal of x square. Its graph also has two disconnected parts. The fact that the graph of a function has some of them have two disconnected parts like this, some of them have a single connected part. It has to do with whether the function is continuous or not. We will see these things, okay, when the time comes. This is the graph of the function y equal to x square. In this case, you can clearly see, just like the one above it, the domain is the set of real numbers from which 0 has been removed, because now also in the denominator we cannot have a 0 term, and the range in this case is the set of all positive real numbers, not non-negative, simply because the graph or the two parts of it lie above the x-axis does not make it non-negative. For the range to be non-negative, 0 should actually be in the range. 0 should be an output. But here, for no value of x will you get y equal to 0. So the range is the open interval 0, infinity. And finally, Oh, but there is this other one also. Two more are there. This one is only on one side of the y-axis. The function is y equal to x to the power 3 by 2. Since square root is involved, so negative values of x are not allowed, and the function also is positive. It becomes 0, of course, at one point where x is 0, y also is 0. For other values of x, for positive values of x, y is also positive, because we have chosen what is this? This is the cube of the positive square root of x. For any non-negative real number, there are two square roots, minus square root of x and plus square root of x. If you take the square of both of them, you get x. But when you see this or this, that is the positive version. If you want the negative square root, you have to write like this. That is also there, that is also a function. So this is nothing but this. Okay, so in this case, the domain is the set of non-negative real numbers. See the difference between this and this. Here 0 is not an output, but here 0 is an output. The graph actually touches the x-axis. Here the graph, or the two parts of the graph, don't touch the x-axis ever. And range, oh no, sorry, what I was saying about just now is about the range. Here the range is 0, infinity, and here the range, sorry about that. The domain, of course, is this, but the range is also this. Yeah, these two things are different. And now we see some straight lines. We have already learned some things about straight lines, their equations, the different forms of the equation of a straight line. So we can now draw some graphs of straight line equations, or some straight lines passing through the origin, and some values are given here. So we will just draw them here roughly. This one is y equal to x. The others I am going to draw not becoming that careful. This is y equal to 1 by 2 over x. This, of course, is the x-axis, this is the y-axis. And then we have a very steep one, y equal to 3x, and in the text the equations haven't been written here, but only the slopes of the lines have been written. Anyway, this is y equal to minus 2x. When you see negative slope, here the slope is minus 2, the line will be like this. If the slope is positive, the line will be like this. Because if slope is positive, then we already know that the graph or the line rises upwards towards the right side. And if the slope is negative, the line sorry what the hell am I saying, the line goes down. Okay, it dips if we go towards the positive side of the x-axis. So this is minus x, and then perpendicular to this line, or I should not have drawn it like this. Let us change it, let us make it a little bit more steep. This is only to show the lines together. Okay, obviously I only drew this one y equal to x carefully. The others I am just simply drawing, showing which one will lie in what position relative to the others. So this is y equal to minus x, and then perpendicular to this is y equal to minus x, that is y equal to minus 2x. And here all the equations are of the form y equal to mx for selected values of m. The domain is R and the range is also R. What would happen if we take y equal to 0? Then the line will be this. In that case, the domain will be R, but the range will consist of the single real number 0, because the graph is the x-axis itself. And if you take the y-axis, that is also a line, it also has an equation x equal to 0, but it's not the graph of a function, because it fails that vertical line test. For that single point 0, you have infinitely many values of y satisfying the equation of the satisfying the given equation x equal to 0. In fact, you can take any value of y. So that is not, this is not the graph, and this is a graph, but its range is only this. For the other straight lines, they are graphs of the function y equal to mx, where the domain and range are both equal to the set of real numbers. Next, let us see one more thing. Just like numbers, we can add, multiply, subtract and divide functions. Sums, differences, products and quotients of functions. Like numbers, functions can be added, subtracted, multiplied, and divided, provided of course the denominator is non-zero, except when the denominator is 0 to produce new functions. This can be done only, at this stage I can say just that, only for real valued functions, because we use the operations of addition, subtraction, multiplication and division of real numbers to define these things: addition, subtraction, multiplication and division of functions, real valued functions. For other types of functions where the output is not necessarily a number, such notions are not always available. That is, we cannot just add any two functions. It should make sense, or it should somehow be useful. This type of things, that is, sum of two functions or product of two functions, they arise so often that the mathematicians have decided to define the concept properly so that it can be studied. If f and g are functions means real valued functions, that is understood, that is the only type of functions we are considering here, then for every x that belongs to the domains of both f and g. Say their domains have a common point, or they have a non-empty intersection from where we are choosing one common input x. We define the function f plus g, the functions f plus g, f minus g and fg. The sum of f and g, the difference of f and g, f minus g, and the product of f and g by the formulas, by these formulas, which are very natural, you will see. F plus g is a function whose value at x is defined to be f of x plus g of x. That's why we need the functions themselves to be real valued, so that it makes sense to add f of x and g of x. These two are real numbers. Okay, and this is defined to be the value of the function f plus g at the point x, and x needs to be in the domain of both f and g to make these expressions well defined. Because if x is, for example, not in the domain of g, then g of x does not make sense. Or for that matter, if x does not belong to the domain of f, then f of x does not make sense. So for both of these symbols to have some sort of meaning, we need x to belong to the domains of both f and g, and for that the domains of f and g should intersect should have some intersection in the first place, otherwise this function cannot be defined. Okay, so this is one. Then correspondingly, the others are defined similarly. Where addition, subtraction and product of real numbers have been used in these definitions. At any point x belonging to the intersection of this is the notation for the domain of the function f. We have already used it before. And the domain of g such that g of x is not equal to 0, we define the function f by g as f by g is a function whose value at x is defined to be f of x. When we define something, we write like colons like this. The term that lies on the side of the colon, that is the term being defined, and its meaning lies on the other side where we don't have the colon. Sometimes we use this notation like this also. Then also same, you have something here and you have something else here. This is the thing being defined and its meaning is this. Okay, so when you see an equation and you see a colon like this, you know what is the thing that is being defined and in terms of what it is being defined. So f by g at x, it means this. Since g of x is non-zero, so this quotient makes sense. You can divide the real number f of x by g of x. Functions can also be multiplied by constants if c is any real number then we define the function cf as cf, we have multiplied the function f by the real number c at x to be the product of the real number c and the real number f of x for all x belonging to the domain of f. Now in example 5, we have two concrete functions and their sums, differences and all those things along with their corresponding domains. So it's a sort of table. So the function is given here, and then its formula appears here in this column, and the domain appears here. The vertical lines are not there in the text, but of course the text is a printed thing. So to distinguish between things, we are putting vertical line. Suppose we have f and g. The formula for f is f of x is square root of x, and g of x is square root of 1 minus x. Since we have square root, here the domain is the set of all non-negative real numbers. For this one, 1 minus x should be non-negative. That means x should be less than or equal to 1. That is just the condition. F should be less than or equal to 1. So x can be negative also. Here x can be negative, there x is not allowed to be negative. So here the domain is minus infinity comma 1, but since you can also take the value 1, so you have closed on this side. Okay, it's a closed ray. So these are our two functions, f and g. So now we just calculate. First of all, we see what 3g is. It is defined at x by this formula. By first of all using the definition of 3g and then using the formula for g. Just like the domain of this one, here also we just have to bother about this term under the radical sign. We don't really care about what 3 is doing here, at least when we are calculating the domain. When we are calculating the range, of course, you have to find all the output values. There, the set of all output values is the range. Then 3 will play a role. For calculating domain, 3 does not play any role. So here again the domain is this, and then sum of f and g, f plus g. Its formula we know, it will be this. And this will this formula makes sense only for those x that belong to the domain of f as well as the domain of g. So here the domain is the intersection of these two things, that is nothing but the closed interval 0, 1. Then f minus g, same domain, but formula of course will be different. Okay, after f minus g we have g minus f. Yes, that difference can also be formed. This does not affect the domain, it does not change the situation, it still stays 0, 1. Then f dot g means fg. Fg of x is f of x times g of x. Here also we should have the common domain 0, 1 common to both f and g. Then two more possibilities are there, f divided by g. For this we should not only consider the points that are common to the domains of f and g, that is these points, but we should also consider the fact that g of x should not be equal to 0. Now when is gx becoming 0? This expression becomes 0 only when x is 1. So we cannot consider 1 here. Let us first write the formula. F by g of x is square root of x divided by square root of 1 minus x, and the domain here is the half open interval 0, 1. And there is one more possibility. You can also form g divided by f, which we will simply write here. G by f in this case we are not allowed to put x equal to 0. So from this common domain we have to remove 0, we have to weed it out, we have to yeet it. So this is the common domain. After this there are some texts written here that x equal to 1 has been included, x equal to 0 has been included from this, which is there in the text. You can understand what we have done here. After this there are some other notions of even and odd functions, and then composition of two functions, which is very important, we will see that, and some special types of functions, greatest integer function, absolute value function we have already of course got. So we will see those things and then we will start solving the exercises. So I end the video here itself. If you want to comment, you can of course comment in the comment section. If you like these things, please consider subscribing. So that will be all in calculus. So see you in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice day.